Okay, well, thank you very much indeed for asking me to talk to you today. I thought I'd start with a snap. That clear? Can we get the lights off the front of the screen? Is that possible? To talk. First of all, have a slide up from the field investigation I took part in 2011. This is me standing outside a school on Arahama Beach. So it's not just like a holiday snap. This slide actually has a purpose. This is actually what's called a vertical evacuation structure. So it's actually a school on Arahama Beach where hundreds of kids actually evacuated to the roof of the building and then were evacuated by Army helicopters within a day or two. As you can see probably from some of the damage, the tsunami wave reached the first floor and even the second floor of this building. And this is the devastation surrounding the school on Arahama Beach. This is looking towards the sea. So if it'd be behind us or that direction, there's a motorway bridge, quite some distance. But basically, if you made it to the motorway bridge, you survived, and if you didn't, you died, and many hundreds of people died here. But the school kids were saved, and not just the school kids here. There are many other schools built as vertical evacuation structures, some really very cleverly designed, sort of pointed towards the seafront, so deflecting the tsunami wave as it comes in. See, the backwash from a tsunami can carry bits of ship with it and things like that. So they might build a gym on the back as a sacrificial structure to protect the evacuees. So I think the first point to note is that Japan is actually in many ways a very well prepared society. Probably less than 20,000 people died in this catastrophe. When you compare that to, for instance, the Indian Ocean Boxing Day tsunami, where maybe 250,000 people died, I think it just gives you the level of the differences in the level of preparedness. So I think that should be our first thought. Japan, by and large, is a very well prepared society for disasters, and we should sort of bear that in mind as we start. Before we move on, just want to make a few acknowledgements. The EFIT team, this is the Earthquake Engineering Field Investigation team of the UK Institution of Structural Engineers, various IRDR PhD students. Mitsuyasu Onaka had been my host a couple of times at the Earthquake Research Institute at Tokyo University. Toshiyuki Hashida, who hosted me at Tohoku University on many occasions, and then a number of people actually helped me with the preparation of the talk itself. But starting back in history, and the reason why I was asked to give this talk is that this is the 150th anniversary of the so-called Choshu 5 coming to UCL to study science and engineering, and there have been a whole number of events throughout the year commemorating this, including an event the Institute for Risk and Disaster Reduction is putting on later this year, later this week as well. UCL obviously somewhat a different place, as we can see. The Choshu 5 became instrumental in leading the Meiji Restoration, which was the revolution which overthrew the military dictatorship, the shogunate in Japan, and established Japan as a modern democracy. And one of the Choshu 5 went on to become the first Prime Minister of modern Japan, Ito Hirobumi. And just to note that UCL has its long association, so Prime Minister Koizumi also was a UCL alumnus many years later. But I think when we're talking about culture, we often look at history. When we look at disasters, rarely do we really look back in history and learn from disasters. If you are a member of a general staff, you probably would know all about Thucydides, Peloponnesian Wars, you probably know all of Napoleon's campaigns. But when we talk about disasters, we rarely know much about preceding disasters. And there's always this chance of making the same old mistakes. So even though I'm going to look forward, I'm actually going to start by looking back. And I'm going to look back, first of all, to the great Kanto earthquake, a major earthquake which devastated Tokyo in 1923. This image here is of western Tokyo looking towards Yokohama with obviously almost complete devastation. Refugees crowded into the grounds of the Imperial Palace for safety. Almost 100,000 people died, 3.5 million made homeless. I also put up this woodcutters as well, showing sort of a heavy rain or cyclone coming over. So I think what's important to understand about the Great Kanto earthquake, it wasn't a single earthquake event. It was a cascading crisis. You had an earthquake, the Tsunami trough, you had a landslide, there's a small tsunami, but the earthquake itself started fires. But probably if it hadn't been for the cyclone off the Kanto and Noto peninsulas whipping up the fires into a firestorm, the devastation of Tokyo wouldn't have been so total. So you have cascading crises. This idea a crisis starts somewhere, but actually we don't know where it's going to finish. There are major social ramifications in the earthquake as well. Following the earthquake, there's this massacre of ethnic Koreans who are blamed in one way or another for the earthquake and its consequences. And there are political assassinations by the police and army. So this is Noito, a notable radical and feminist who was beaten, killed and thrown down a well by the military police. Lieutenant Arakazu, who went on then to become a leading figure in the later military government in Japan. So I mean, you have a natural disaster that actually has social consequences through a whole series of cascading events. Moving on to the Kobe earthquake, called it the wrong earthquake. This is an image here of what's called the seismic gap theory. This was seismic gap theory is a theory by someone called Hiro Mogi, who happened to be the boss of my supervisor at Tokyo University, Mitiyasu Onaka. And the idea was that where you had an absence of a major earthquake on a fault, this was a likely place to have a fault, to have a major earthquake. So Japan's earthquake prediction program was focused on what was called the Tokai earthquake, which is close to Tokyo and what is eastern Japan. There's similar earthquake prediction experiments going on in America and China and Europe at the same time. But what actually happened then was an earthquake occurred in Kobe in western Japan. Now, it's actually the first sort of earthquake I visited with one of my first PhD student, Nitra Dedra. So the earthquake fault doesn't look like much, just sort of 1 meter offset at the edge of a rice field. And while in eastern Japan, the population was well prepared, you had these trucks going around, with earthquake simulators on them. This is the control room of the Tokyo Metropolitan government up in Shinjuku to actually manage a disaster. Comparable preparation really didn't exist in Western Japan. Actually, my sister-in-law was a teacher at Kobe High School at the time, and many of her students and staff actually died in the earthquake. And there was no preparation. They didn't have water under the sink and torches to hand as we did, who were living in Tokyo. The consequence of this was actually there's probably a collapse in the Japanese earthquake prediction program, a loss of confidence that natural scientists could deliver the answers. And this was echoed around the world. The US earthquake prediction program similarly was shut down. Only the Chinese, the Greeks, and probably the Romanians sort of kept something similar still in place. And then I guess this brings us more up to date with Fukushima, where I sort of should perhaps be the starting point for this talk. So this is the Fukushima Daiichi nuclear plant on the Pacific coast of Japan. You can see 4 reactor units very close to the sea, and on a bit higher ground, reactors 5 and 6. You can probably see there's a baseball pitch up there as well, and if you think if reactors 1 to 4 had actually been built where the baseball pitch is, Fukushima would not be a word now sort of renowned around the world. This is the tsunami wave which came over, a very well-known image. It simply went over the 6 to 7 metre high tsunami wall defending the reactors. These are measurements of the run-up and of the inundation along the Japanese coast. This is the Fukushima area. Further up is Sanriku and then the Hokkaido coast. And you can see measurements of height, both the run-up height and the inundation. This dashed line shows the inadequate Fukushima wall, so 6 to 7 metres high, and again the wave simply went over the top of it. Though actually further up the coast you can see the tsunami wave was substantially higher, even up to 20 metres and more. This was part of our first report in 2011, so it's this current state, but actually that's 2 years old now. The knock-on consequence was a large-scale shutdown of the Japanese nuclear industry, and as we know, a general loss of trust in the global nuclear industry. Very few countries are actually building nuclear reactors now. Even China scaled back its nuclear program. And of course, what then shook the world were the hydrogen gas explosions in the reactors 1 to 4, which all suffered some sort of damage from explosions. But again, Fukushima is another cascading crisis. We visited Fukushima. We couldn't visit in 2011. The radiation was too high, but we visited in 2012 in a trip arranged for us by the British Embassy. This is the number 2 reactor. So we're in this bus, and the driver sort of puts his foot right down, went past a high speed. We've still got that. That's when we got all our dose of radiation anyway. So that's a highly radioactive reactor there. Now this is a picture here of a collapsed pylon. So even though there was an earthquake and there's a tsunami, it was actually really a landslide which did for Fukushima. This landslide cut off Fukushima from the national grid. Nuclear reactors are cooled by pumps, really quite similar pumps, simple pumps. These are pumps we've just photographed on the back of the lorry. I think they had 2 lorries here with pumps. Actually thought wisely now to actually site another of these lorries up there, a bit further up the hill. Very simple pumps, but simply the batteries ran out of those pumps. The reactors went into meltdown because of lack of cooling, and then that triggered the hydrogen explosions. This is inside the control room in Fukushima. It had just been built to be earthquake resilient, but the hydrogen explosions actually ripped through the fabric of the building, exposing all the workers to very high dosage of radioactivity. So these guys are actually very brave. They're back there working. Sort of a bit of an inverse situation. In Japan, there's a law that says that you can't work in the nuclear power industry if you've had a certain exposure to radiation. Well, basically, their nuclear power industry wouldn't work if they really enforced that. So what they've done is sort of make the control room itself sort of a radioactive free, and you have to do all this sort of scrubbing and having your fingers and toes sort of tested for radioactivity before you actually enter their environment, which is now sort of trying to be safe for them to work in. I think what's notable about this is actually the whole nuclear power station is just run by Toshiba laptops, the sort of slightly aging computers we tend to have in laboratories to run old bits of kit which we don't really want to upgrade because it works all right, so you just keep things going. We weren't allowed to take pictures ourselves. We asked TEPCO to take pictures for us, but we weren't allowed to take pictures ourselves. So I'm afraid this is a picture I pulled from the web. This is a pressure gauge, a mechanical pressure gauge. the workers no longer trusted their instrumentation that was clear sufficiently, and actually how they were monitoring the pressure inside the reactor was a mechanical pressure gauge. They simply set up a camera on the mechanical pressure gauge. I have a lot of sympathy with this. If anybody knows me, I've built many high-pressure systems. My PhD supervisor said, always put in a mechanical pressure gauge into the system. You can't necessarily trust the programmer, the software, the instrumentation. Always have something there that you can believe. And after the disaster, they obviously did exactly this themselves. They put a camera on a mechanical pressure gauge. But Fukushima then led to, I think, probably a crisis in Japanese science. So there are a couple of headlines here, both from Asahi Shimbun, popular large circulation newspapers in Japan. On the far side, it says, don't ignore, the headlines, don't ignore the root of distrust. And then the editorial goes on to argue that nuclear scientists are part of a ring of distrust, which consists of electricity companies, politics, policy making, and the media. And on the other side, from Asahi Shimbun this year, again, an interview with a university professor, with the title saying, a nation where science and technology is distrusted. And in the interview, the professor goes on to say, Japan has a view that science and technology cannot fully perform its purpose in policy making, which actually in Japanese society is a very strong statement, actually, of the distrust of science. So we have this ongoing crisis in Japan in science, technology, and engineering. But there are other views. This is from the Carnegie Institute, Washington, D.C. Why Fukushima was preventable. And as far as I can see, I take this to be a restatement of orthodoxy. The idea that if we just knew enough, if we were just a little bit more certain, if we'd just done one more experiment, if the Japanese were just complying a bit better with international standards, this disaster wouldn't have happened. And so I want to sort of just look at this disaster, because I think it's probably, it is sort of, I think, good to understand this. We've got these two conflicting points of view. Something being put out saying it was preventable, the idea you've got a crisis in Japanese science. And we need to ask some questions. Just before I go on, I'll just say something briefly about the plate tectonic background of Japan. So we all know plate tectonics, the idea that the Pacific Ocean is spreading from the center. On the eastern side, the plate is subducting under the American continent. On the western side, it is subducting. As it subducts, you get the release of volatiles. They create stratovolcanoes. The stratovolcanoes are the island arc, which are Japan. And these are the plates around Japan. I've said the changing geological setting of Japan. Of course, the geological setting of Japan isn't changing at all. But it's very interesting. I think when Fukushima was built, the Tohoku would have been considered to be on the Eurasian plate. Tohoku was then put on the North American plate, and now it's sort of got its own little plate of its own called the Okhotsk plate. So it's fairly fundamental in geological terms if you don't even understand the big-scale tectonic setting. So the big-scale tectonic setting really was probably not understood at the time Fukushima was built. Now, was the earthquake forecast? There are obviously some claims that it was. Again, sorry, this is all Japanese, but I think it should be fairly obvious what the figure is. You've got the map of Japan, you've got the major Japan Trench going down the eastern flank, and what this figure is showing is a whole series of segments of the fault. And the theory was that probably only one or two segments of the fault would rupture at any one time, giving sort of maximum magnitude earthquakes of 7 to 8. And what actually happened was all 6 segments ruptured at the same time, creating this mega event. Now, could the earthquake have been forecast? It's probably a far more pertinent question. Again, that on the left, we have what's called a slip deficit map. So this is how much of how much slip should have occurred on a fault, but it hasn't. So ignore the dots, just look at like the red shading, which is the slip deficit. But this very large area of slip deficit off the Tohoku coast, another area of slip deficit off the Hokkaido coast. There was a major Hokkaido earthquake. If we look on the right-hand side of the aftershocks of the Tohoku earthquake, the aftershocks, these yellow dots, sort of map out the fault plane of the fault. I think by comparing the yellow dots with the big red area, I think it's quite clear to see the slip deficit and the fault match up very well. So in this sense, the earthquake itself, the magnitude of the earthquake, could have been predicted. But what about the tsunami? Again, in that Carnegie report, they go back to saying, if we had just better understood the sediment deposits, it would have been possible to understand that there could be these large tsunami. So we know there was a backwash and this huge wave, 10 meters high and more, came in 30 to 40 minutes later, bringing devastation with it. Now, the Sanriku coast has had devastating tsunami in the past, notably 1896, 1933, and the 1960 Chilean earthquakes. But there, the wave heights were a matter of a few meters, maybe 4 or 5 meters. So nobody really expected such a high tsunami. There had been the Jogan earthquake and tsunami of 869, and a further one at 1611, where there's evidence that there were higher tsunami waves based on the inundation of the Sendai Plain. I went out in the field with sedimentologists. These sort of things do interest me. I looked at the sedimentary deposit. This is of the Tohoku tsunami of 2011. Now, tsunami deposits, they can be massive, they can be laminated. Yes, you can identify them. We are identifying a tsunami deposit which has just been laid down. I think it is highly unlikely that policymakers really would be making policy decisions based on tsunami sediment deposits from the Jogan period. So I'm highly skeptical of this view that somehow if we had just a bit more knowledge about the sedimentary deposits, we would have understood better about this earthquake. And the models of tsunami generation have just changed as well. Dan Mackenzie and James Jackson came out with a new theory to explain why you get such a high tsunami wave. You used existing theories of how tsunami are generated. The elastic rebound of the crust just doesn't give you a high enough wave. So their theory is that as the Pacific crust subducts underneath this accretionary wedge, you get this little pop-out occurring. It sort of, just literally pops out. You see that little yellow wedge popping out. It is that which is generating the high tsunami wave. But this is a new theory of 2012 coming out from the earthquake. This is not old theory. So the theory also was not in place to predict such a high tsunami wave. What about engineering preparedness? This is Taro. This is halfway up the Sanriku coast. What we have here, you can see the first line of sea defences looking out into the ocean, a second line of sea defences close to you. We pan back, obviously some has been cleared by bulldozers. We were there sort of 2 months after the tsunami, but you can see the devastation that actually had occurred. And behind us, again, a further tsunami wall, which is 10 meters high, but the tsunami had simply overtopped it. Locally, these walls were known as the Great Wall of China because they were so massive and so imposing. Unfortunately, the population sheltered behind these walls, by and large, didn't evacuate, believing that they were safe behind their walls, and died in their thousands when the tsunami overtopped the walls. I say, when you go to somewhere like Taro and you look at Taro, you are really led to believe that, these are such enormous structures, what is really quite a small fishing village, that you cannot pour enough concrete to defend yourself. It is really something that you cannot do. So what is next? Then I think you might say, what then about the the warning systems, and social preparedness. So this warning systems basically set up on the idea that electric wave travels faster than an earthquake wave or a tsunami wave, so you can get some sort of warning to people before the arrival of either the earthquake wave or the tsunami wave. There were significant errors in the warnings issued, as I think probably everybody knows. The first warnings came in that the tsunami wave was going to be a matter of 2 meters or so. Later warnings were more effective, and certainly the far-field warning going out across the Pacific was effective. But I think we can say that before the Tohoku earthquake, they had estimated there would be about 8,000 deaths from an event like this. As it was, there are a little more than double that number. The warnings and evacuations did fail in part, but also I think they succeeded also to a very large extent. In some towns we visited, the evacuation drill rehearsals, the take-up was between sort of 30 and 60% prior to the tsunami. So you actually did have an educated, informed population, and by and large, they did evacuate. There's another issue of how slowly you might evacuate or where you evacuate to, but by and large, the populations did evacuate. So this did undoubtedly save lives. Also, the law had been changed. For the Kobe earthquake, the army was simply not allowed to operate in Japan. The law was changed. The army was allowed to operate in the Tohoku region, even without direct orders from Tokyo. It's somewhat surprising if you know Japan. They were there right at the outset, rescuing people and lifting kids off of school roofs. So again, the recovery process was almost immediately went into effect. So there were errors, but there are also successes as well. So this sort of brings me to my conclusions. I don't have a clock here, so I'm not quite sure how fast I'm going. But I think there are things that we need to think about. Firstly, there's the evacuations. In Fukushima, it is estimated about 1,500 people probably died from being evacuated as a consequence of being evacuated, which is probably about the same sort of number who died actually directly from the earthquake and tsunami. So I think one thing we have to think about is, do we need to have these blanket evacuations? Would it be better sort of maintain older people in their homes rather than unnecessarily evacuating them? And I think we need to have a far more flexible response in the immediate aftermath of a disaster, and to better understand the needs of the elderly and of the disabled. For ourselves and we are collaborating with a new institute set up at Hoku University, the International Research Institute for Disaster Science. So again, this is a major investment from the Japanese government, and this institute is certainly different in its concept. We're holding a joint symposium on Thursday with them at UCL, and a workshop on Friday. The idea that the institute should be outward-looking and also have a strong regional focus as well, to work with countries in Eastern and Southern Asia as well. Again, I think probably fairly new in many ways for Japan, that's such a large-scale commitment to internationalism and regionalism. I think there has to be a questioning of whether just pouring concrete and building structures really is effective, and is this the real way to build resilient societies? I think international solidarity is important. I think these are paper cranes sent by school children in Italy to the Ofunato ward office. Technology will have its role to play. I think the increased use of satellite technology will become an important factor. So technology has to be used, has to be grabbed, has to be seized, but we have to understand what that is doing in terms of the social resilience that we're trying to build. Finally, of course, there are other disasters. So this is the typhoon that hit the Philippines. And I should just mention that I've been asked by the UCL Union Volunteering Society just to mention this. They have an event this Friday, which you'll probably find out about on their website, and they're part of a fundraising drive. They also asked me, if you wish to donate to the Disasters Emergency Committee, the easiest way to do that is just to type text HELP to 70,000, and that gives £5 to the Disasters Emergency Committee. So I finish with a picture postcard shot of Mount Fuji, and probably take myself back to where I started off. The idea, as we know, that generals always fight the last war and the last battle rather than looking for the new one. But we know that natural hazards are complex events and they're cascading events. There's some reasonable evidence that earthquakes off the Nankai Trough, off of the southern part of Japan close to Tokyo, can actually trigger eruptions of Mount Fuji. We can actually imagine a complex event where we have an earthquake, maybe a tsunami, and somewhat later on a triggered eruption of Mount Fuji, creating a cascading crisis. So we shouldn't be thinking too much about the Tohoku earthquake. We need to learn the lessons, but we think we also need to understand how can we grapple with the idea of these cascading complex crises. Okay, thank you.
Thank you very much, Peter. That's fascinating. We've got 3 or 4 minutes for questions. Thank you very much.
Thank you very much for all of it. But could I just come back to your almost opening remark about of the 20,000 who died in the tsunami, that if you reached a certain motorway bridge you lived, and if you didn't you died. And it does seem to have been as absolute as that. In other words, that once one is naked of defences to a tsunami, there don't seem to be any tales of anybody surviving. You would think from a dynamics point of view, some bodies which are buoyant would be thrown up and survive. Given that if you're on a boat you hardly notice it, hasn't much been done on the sort of the dynamics of what happened to a tsunami once it's breached a coastal defence, and in relation to either personal surviving, as in avalanches, or in how you should pour the concrete to defend?
Well, first I'll say that I think if you're caught in the tsunami and your chances of survival are very, very remote, it's simply not like an earthquake where you expect a whole range of percentage of casualties depending on buildings and structures and all the rest. I mean, you have to evacuate, whether that's vertically or whether that's along to a safer place of refuge. I think the interesting things are the disparities in responses. So there's a 40-minute warning, basically, for the tsunami. If you're over 50, it takes you about 20 minutes to decide to evacuate. You're probably a bit slower as well, so you've only got 20 minutes. So I mean, you're obviously more likely to die if you're older, just because you have that 20-minute decision-making time. I don't know why it is. It might be, you're concerned about the grandkids at school. You might have a whole host of concerns, whilst younger people do seem to act more immediately on the actions. But I think it is really this sort of the social resilience, trying to understand people's behaviour before the tsunami is probably the most important thing for helping them survive.
Other questions?
Thanks. I was interested in what you said about the difference in preparedness between East and West Japan, and I'm not sure I completely understood the argument. Is it because on one side people had more memory of previous disasters, so they prepared more, or was it a general understanding of this, like the general population understood this seismic gap theory, and that if there hadn't been an event they should prepare, or was it a national strategy to invest more in preparedness in certain places?
I think it's all three of those, and obviously I'm talking about 20 years back plus, and things have changed. But certainly, if you spoke to people living in Western Japan, like, late 1980s, early 1990s, they didn't really believe that they were living in this such vulnerable area, even though if you look back at the historical record, there were significant earthquakes.
One more, if there's... Yes, right up at the top.
Hi, yeah. I'm just interested about the kind of nuclear fallout element of the disaster. And obviously they're trying to remove the nuclear rods at the moment of one of the reactors, but there's 3 that the radiation is still too high to do anything about it. And I've also read reports about if there was to be another earthquake and the effect of that, and even talks about they would have to evacuate the west coast of America. What are the sort of basis of those are they sensationalist writings about the threat of nuclear fallout moving globally across the oceans?
Well, I'd say I'm not a nuclear expert, but my understanding is that the reactors 1 to 3 obviously suffered core meltdown to some extent. And certainly for one of those, that took a very, very long time to stabilize. And I don't believe even now people really know if one of those is stabilized or not. The reactor 4 was already, I think, shut down for maintenance or something like that. So it was in a different condition. And obviously the idea that should for some reason the cooling be disrupted again, then it could trigger another event. But as I say, that there does seem to be more resilient structures. As I say, they've got these pumps on trucks. They've got another one just parked up a bit further up the hill. They've got better batteries there. They're reconnected to the national grid. It seems like they can keep the cooling going. But in a sense, there are other issues. They've got all this waste radioactive coolant now stored in these tanks. We know that they are leaking. That has become another issue. Yes, it would be very, very unfortunate if there was another major catastrophe there. But in terms of risk, it's probably not that likely. But as I was saying, in these issues, it is very difficult to necessarily quantify risk in this way. You have to start looking at these unmeasurable uncertainties and actually try and understand them in a different way.
Okay, well that's fantastic. Thank you, Peter. Thank you very much. If I could ask you all to thank you in the usual way.